Yes, welcome once again to the class and welcome once again to the channel, and let's start our discussion from here onwards. That we had already learned that first stage rockets cannot attain higher speed for the same total weight and total fuel supply, and the reason behind this was that we had to actually discuss the limitations of single stage rocket, right? So we have successfully actually discussed the limitation of a single stage rocket because it cannot attain speeds higher than 3.5 km per second. So we have successfully explained the limitation of a single stage rocket, and many of you have wished me a happy Guru Purnima yesterday. I am really sorry that I could not answer many of the WhatsApp chats because there were around 350 WhatsApp chats which had come, which I had got in my mobile yesterday. So that's why I was not able to reply to each and every happy Guru Purnima wish. So don't worry, I am with you always, and I respect the I respect the fact that you respect me. Okay. So, and someone had also asked that why do you post some political things on Telegram group. So the thing is that I had initially thought that I will be away from politics, but the thing is, when I saw that only a single ideology people are speaking everywhere and others are keeping quiet because of fear, because of fear everyone else is keeping quiet and only a single political party ideology people, which is the ruling political party, those people are only the ones who are speaking and others are keeping quiet. So that's why I started to put some political stuff so that you get the overall perspective. Okay, although those political stuffs are not important for your IAS examination, but those will give you a perspective towards life, that the life is far much bigger than those of WhatsApp forwards. Okay, life is far much bigger than those of WhatsApp forwards. So let us see the question. Find the velocity of the rocket assuming that gas is ejected at constant rate alpha and at constant velocity with respect to it, and that it moves vertically upwards in a constant gravitational field. Now what does this mean? This simply means that we have to find out the final velocity of the rocket, expression for the velocity of the rocket at any time. We have to assume that the gas ejected from the gas is ejecting at a constant rate alpha, that is the fuels, the mass of the fuel in the rocket, the mass of the fuel in the rocket is reducing at a constant rate alpha. Okay, and at a constant velocity with respect to the rocket, the fuel is getting exhausted and the exhaust gases have a constant velocity with respect to rocket, and and the rocket moves vertically upwards. Okay, so it is perpendicular to the ground. Its direction of propagation, the direction of movement of rocket, that is direction of propagation of rocket, is vertically upwards, that is perpendicular to the ground. Okay, and that too in a constant gravitational field. Okay, because we are assuming that the rocket is not reaching much higher heights, so the gravitational field more or less remains constant for lower heights. Okay, also calculate the total distance traveled by the rocket in time t. We have to also calculate the total distance traveled by the rocket in time t. That is, we have to find the velocity of the rocket in terms of time, and we have to find out the total distance traveled by the rocket in time t. Okay, so we have to find out velocity as a function of time, and we have to find out distance as a function of time. Okay, now as the gas is ejected at a constant rate alpha greater than 0. Okay, we are assuming that your alpha is a constant which is greater than 0, which has been given to us over here, that gas is ejected at a constant rate alpha. So let us assume that gas is ejected at a constant rate alpha which is greater than 0. Then m equal to m naught minus alpha t. Now what does this mean? Actually, m is the mass of the rocket after some time t, and m naught is the initial mass of the rocket. Okay, what is m naught? M naught is the initial mass of the rocket, and m is the mass of the rocket at some certain time t. So we have found out mass of the rocket at a time t in the function of time. We have found out mass of the rocket as a function of time. Now, how did this expression arrive? How did we arrive at this particular expression? So the thing is, when you subtract from the initial mass is m naught. When you subtract alpha t from it, okay, when you subtract alpha t from the initial mass m naught, then certainly you will get the mass at a time t. Why? Because alpha is the rate of change of mass. What is alpha? You can see over here, rate of change of mass. Okay, that will be equal to rate of change of mass with respect to time. So dm by dt, that is equal to minus alpha, and we have assumed that alpha is greater than 0. That's why we have put a minus sign over here, so that we can show that the mass of the rocket is reducing with respect to time because of fuel being exhausted. Okay, so dm by dt equal to minus alpha. So when I write that mass of the rocket at a particular time t equal to m naught minus alpha t, where m naught is the mass of the rocket at t equal to 0, I have simply applied unitary method which is used in the lower classes. If you multiply the rate of change of mass multiplied by time, rate of change of mass multiplied by time will be equal to the mass lost. So what does this imply? This particular expression, what does it imply? It simply implies that this much of mass has been lost. Okay, this much of mass has been lost in the form of ejected exhaust gases of the burnt fuel. Okay, this much mass has been lost in the form of ejected fuel gases. Okay, so this much of mass has been lost from the rocket. So the mass of the rocket at any time t will be equal to m naught minus, you will multiply rate of change of mass with respect to time. When you multiply it by time, how much mass is lost in 1 second when you multiply by number of seconds. So by unitary method you will get the mass lost. Okay, because alpha is the rate of change of mass with respect to time. So how much mass is lost in 1 second, that's what is told by alpha. Okay, how much mass is lost in 1 second, that's what is told by alpha. And when you multiply this alpha by time, what do you get? You certainly get the mass lost. Okay, you certainly get the mass lost. So where m naught is the mass of the rocket at t equal to 0, this m naught is what? It is the mass of the rocket at time t equal to 0. Now, so this expression you got from the unitary method. Now since F external equal to minus mgi, you know this very well, that the gravitational field, constant gravitational field, is the only force acting on the rocket, because there is no air resistance. As the problem does not talk about air resistance. Okay, as the problem does not talk about air resistance, so we will ignore it. Okay, so we remember this thing very well, that whenever you have to consider air resistance, surely the variation of air resistance with velocity will be given to you. Okay, if the examiner wants that you should consider air resistance, then some mathematical law governing the air resistance must be given to you in the problem itself. But over here nothing has been given about air resistance to you, so that's why you can ignore the air resistance in this particular case, because nothing has been said. When nothing has been said about the air resistance, by default we neglect the air resistance. Okay, now F external equal to minus mgi, you know this very well, that the rocket will move upwards. As the rocket will move upwards, so the gravitational pull will act downwards, and if I consider the downward direction to be negative and upward direction to be positive, then what will happen? As the downward direction is negative, so your F external will be equal to minus mg I cap. Now let us consider that this particular direction, that is the direction of propagation of rocket in the upward direction, that is plus I cap direction. Okay, and this particular direction, that is downward direction in which the gravitational field is acting, this particular direction is suppose minus I cap direction. then what will happen, your F external will be equal to minus mg I cap. Okay, and your dm by dt, what will it be equal to? Dm by dt will be equal to minus alpha, because rate of change of mass with respect to time, that will be equal to minus alpha. Okay, because the mass is reducing with time, so dm by dt should be a negative quantity, and we have already assumed that alpha is greater than 0. So eventually we will have to put a minus sign over here in order to show that dm by dt is negative, because the mass is reducing with time. The general equation of rocket motion, what is it given by? The general equation of rocket motion is given by this expression, m dv by dt equal to F external plus u relative dm by dt. So as you can see over here, this particular direction has been considered positive I. This particular direction has been considered as positive I cap, and this particular direction has been considered as negative I cap. Okay, so m dv by dt equal to F external u relative dm by dt. This is the equation of motion of rocket, general equation of rocket motion, which we have already derived in the previous class. Now you know this very well, that u relative, that is the relative velocity of the exhaust gases with respect to rocket. What is this u relative? U relative is the exhaust gases velocity with respect to this particular rocket. Exhaust gases velocity with respect to this particular rocket. So u relative equal to minus v naught I cap. Okay, why minus v naught I cap? This is not given in the question, but in order to show that the u relative is constant, it is given in the question that exhaust velocity is constant. Where is it given? Okay, so it is given that, and at a constant velocity with respect to it. Okay, it is given that at a constant velocity with respect to it. At a constant velocity with respect to it means the fuel gases are being exhausted at a constant velocity with respect to the rocket. Okay, so that's why your u relative will be equal to minus v naught I cap. Okay, so this will be minus I cap direction, and in this particular direction the fuel gases are being exhausted. So in order to show a constant, we are assuming u relative to be minus v naught I cap, because the exhaust velocity of the gases with respect to the rocket, someone sitting in the rocket will find that the exhaust velocities are going in minus I cap direction. So in order to show the negative direction, that is on the downward direction with respect to the rocket, we are writing minus v naught I cap. Okay, so what we can write now, we have considered one direction as positive, another direction is negative. So we can certainly remove the vector signs from this particular expression, and as soon as you remove the vector sign from that particular expression, you get this expression that v will open by positive. Why v will open by positive? Because your rocket is moving in the upward direction, so v vector will open by a positive sign, because plus I cap direction is there. So your v will open by a positive sign, so your vector v opened by a positive sign. Then F external, as it is equal to minus mg. Why will it be equal to minus mg? Because gravitational pull is the only pull acting on this rocket, so minus mg direction is this downward direction. So F external will be equal to minus mg, and u relative, what is it equal to? U relative is minus v naught I cap, so you will put minus v naught in the place of u relative. Okay, and dm by dt, as already found out, we have assumed it to be equal to minus alpha. So this minus and this minus will become plus, this minus and this minus will become plus. So let us see the next step. So what did you get in the next step? You will take m terms one side. Okay, see what did you get? You will take m terms one side. Let me see. Alpha v naught, over here it is alpha v naught. Okay, then m naught minus alpha t g, m naught minus alpha t dv by dt. Okay, so you have done nothing, but you have substituted the value of this m, that is mass of the rocket at a particular time t. So what is mass of the rocket at a particular time t? You can see over here that this is the mass of the rocket at a particular time t, which is m naught minus alpha t. Okay, so you will put m naught minus alpha t in place of this m naught minus alpha t in place of this m. Now how we will understand that we have to do these steps, because you have to find out the value of v and distance traveled, that is the velocity of the rocket at any time t and distance traveled by the rocket at any time t. You have to find out these two expressions. So you have to find out the velocity of the rocket as a function of time and distance traveled by the rocket as a function of time. You have to find out these two things. In order to find those two things, you will substitute in the place of small m. So you will get this expression, because you will consider that your expression comes out to be in terms of t. So that's why you are substituting for m, because m is not constant. But as soon as I write that m naught minus alpha t, you can represent the m in terms of time. You can represent the m in terms of time over here. Constant minus alpha t. M naught is the initial mass which is constant. So in order to get an expression for dv by dt in terms of time, we have actually substituted m naught minus alpha t in terms of in place of m. Okay, we have substituted m naught minus alpha t in place of m, so that we get dv by dt expression as a function of time. Now dv by dt, what will it be equal to? Suppose you m naught minus alpha t, divide both side by m naught minus alpha t, then this m naught minus alpha t will be cancelled, this m naught minus alpha t will cancel, and m naught minus alpha t will come over here. So you have got the same thing. So dv by dt equal to minus g plus alpha v naught minus divided by m naught minus alpha t. Now this dt will go on the right hand side. So what will it become? dv equal to minus g dt alpha v naught dt divided by m naught minus alpha t. Then you will eventually integrate. Okay, so as soon as you integrate the expression, now it is incorrect to say that this dt goes to the right hand side. It is incorrect to say so. Okay, because it is a differential equation. So you, in your mind, you assume that dt is going to the right hand side. In order to imagine in your mind, you assume that the differential dt is going to the right hand side, but that is not the reality. Reality is very different. Reality is that this is the particular differential equation. So we cannot say that this dt will go to the right hand side, because dt is not a number, it is a differential quantity. So it is incorrect to say that dt goes to the right hand side. Okay, so integration dv minus g integration dt plus alpha v naught integration dt by m naught minus alpha t. So this is the expression which you get. Now this integration dv you will get as v, and minus g integration dt you will get as t. Now this particular expression dt by m naught minus alpha t, what will you do? You will eventually apply the logarithmic expression, logarithmic formula. So how will it be written? Hopefully you know the integration of this. I don't think there is any need to tell you the integration of this particular expression. I think you all are mature enough to calculate the integral of this particular integral. The value of this particular integral you can find out by using simple integration laws. Okay, so logarithmic formula comes from this type of expression. Still, if you feel that you will not be able to calculate this, you can certainly comment below this video that I cannot calculate this particular integral. I will certainly help you to solve the problem. So integration of this particular expression, what will it be equal to? It will be equal to this much. Okay, and as the integration is indefinite, we have used basically indefinite integrals. So that is why you will get a constant of integration c1 over here. Now this particular expression is your equation number 1. Now at t equal to 0, v equal to 0. So from equation 1, what do you get? Actually we have to find out the constant of integration c1. So in order to find the constant of integration c1, what will you do? You will actually put the boundary conditions. You know this very well that in indefinite integrals you many a times get a constant of integration, and in that constant of integration which you get after indefinite integration, that you can find out with the help of boundary conditions. So at t equal to 0, v equal to 0. So from equation 1, what do you get? When you put t equal to 0 over here, this expression will vanish. When you put v equal to 0 over here, this expression will vanish. So at t equal to 0, v equal to 0, you know this very well, that at time t equal to 0, the rocket takes off from rest. Okay, at t equal to 0, time t equal to 0, the rocket takes off from rest. So that's why v equal to 0 at t equal to 0 you will put. So this expression will vanish, this expression will vanish, and you will get minus v naught ln m naught and t equal to 0, so ln m naught plus c1. So you got the value of constant of integration from here, v naught ln m naught. Now this c1 value you will substitute in the equation 1. So this particular c1 value, as soon as you substitute it in the equation 1, what do you get? As soon as you substitute that in equation 1, you get something of this kind. And after that, over here log a minus log b formula you will apply. And after you apply the log a minus log b formula, you get an expression of this kind. I don't think there is any need to explain the mathematical steps. Those are quite simple. So this is the expression which you get. So from equation 2, what do you get now? I think one of the slides is missing over here. Let me see, just a second friends. Okay, I think one of the slides has been missing over here, which I need to see at the moment. Just a second, wait just a second, okay. Just a second friends, just a second. No, nothing is missing, everything is fine, okay. No slide is missing over here, everything is good. Okay, I thought that particular slide might be missing from here. So from equation 2, what do you get? Particularly from this equation 2, you can write this v as ds by dt. Okay, you can write this particular velocity term as rate of change of displacement, because velocity is equal to rate of change of displacement. So you can write this v in terms of s. So ds by dt you can write. So let us see. So you have written ds by dt equal to, the right hand side is as it is, minus gt v naught ln m naught by m naught minus alpha t. So this is the expression which you get. Now again we will now in this particular case let us use definite integration. But in the examination, remember that over here, in order to find the velocity expression, what did you do? In order to find the expression for velocity, you actually in order to find this expression of velocity, you actually used indefinite integration over here. Okay, you actually used what? Indefinite integration you used. Okay, let me write plus c1 over here. So you used indefinite integration over here in this particular step, but you could have used definite integration also. You could have used definite integration also in this particular step. But if you have used definite integration in the examination, if you used definite integration in order to calculate v, then s also you should calculate in terms of definite integration. And if you calculate v in terms of indefinite integration, then you should calculate s also in terms of indefinite integration only. For your convenience, I have shown one of the integration as indefinite and another as definite. That is, I have calculated velocity by indefinite integration and I am calculating displacement by definite integration. So it is my choice. But in the examination, if you have calculated velocity by indefinite integration, then displacement should also be calculated in indefinite integration. And if you have calculated velocity by definite integration method, then you should calculate displacement also by definite integration method only. Okay, so these are the things you must remember. Now deliberately I have calculated S via definite integration. You could have used indefinite too. Okay, so both the methods work over here. If you calculate by definite integration, then what will happen? If you calculate by definite integration, then no constant of integration will arise. If you calculate by definite integration, no constant of integration will arise. But if you calculate by indefinite integration, then certainly constant of integration will arise. Okay, so on integrating 0 to s, from 0 to s, so this ds from 0 to s you will get, and this dt will go to the right hand side. That means I am just calling it for the sake of convenience. Otherwise there is no such thing that dt is going to the right hand side. Only thing is this particular expression is equal to this expression. That is the only reality. Okay, so 0 to s ds minus g, 0 to t dt v naught, 0 to t ln m naught. Now I have written ln m naught minus ln m naught minus alpha t. So log a by b equal to log a minus log b I have used. Okay, and obviously integration from 0 to t will be there, and this dt expression will remain. Okay, then what will happen? This kind of expression will again come. Now how did you get this expression? How did you get this expression? You have actually, this is constant, so it will be multiplied by t, and this particular integral you all know how to find it out. Okay, this particular integral we can find out with the help of this expression, integration ln dx x ln x minus x. Now how did this particular expression arise? From where did this expression come? This expression came from integration by parts. Okay, this expression came from integration by parts. So you have ln x with you, so you can write it to be ln x multiplied by 1 dx, ln x multiplied by 1 dx. Now when you integrate by parts, that is part 1 will be your ln x and part 2 will be your 1, and you apply the integration by parts, then you will certainly get x ln x minus x. But in the examination, do not use integration by parts. It will be very tedious. You have to directly mug up the result of this. That is integration ln x dx. That comes out to be equal to x ln x minus x. So this result must be in your mind while calculating this particular integral. While calculating this particular integral, this particular expression, that is integration ln x dx equal to x ln x minus x, this particular expression must be in your mind. So you have to mug up such results, and by practice you must remember such results. Okay, so as equal to minus half gt square v naught ln m naught t plus v naught by alpha, and by applying this particular rule we will get an expression of this kind. Okay, so I don't think there is any need to explain the integration steps. Those are quite easy. So you got this expression. Then what will you do? Then what will you do? You have got this particular expression. Then this expression will come. Okay, so I am ignoring the mathematical steps. Then this expression will come, and finally you get the final expression which is written over here. So what kind of steps you have used over here? First of all, you used this formula in the green box, then you did this thing, then what is done? Then this alpha has been put inside the bracket, okay, in order to simplify the expression. Then what has been done? Then is equal to minus half gt square v naught, okay, and this particular expression. Okay, so you get finally this, that is the expression for displacement of the rocket. Now remember this thing very well, that in this particular case the displacement will be equal to the distance travelled by the rocket. In the question it has been asked that you have to calculate the distance travelled by the rocket in terms of time, but we have the expression for displacement of the rocket in terms of time. So will displacement and distance be equal from over here? Will displacement and distance be equal over here? Yes, certainly displacement and distance will be equal over here, certainly. Why? Because the rocket is traveling in a straight line upwards, and the rocket, as it is traveling in a straight line upwards, so it is a rectilinear motion in a single direction, and whenever there is rectilinear motion, that is motion in a straight line, and that too without changing the direction of motion, only in a single direction, whenever such a kind of situation is there, certainly distance and displacement are the same in that case. So this will be your expression. This will be your expression for distance as well as displacement, okay, in terms of time. If you have any doubt, suppose you must try these integrations yourself. You must note it down in your notebook and try these integrations, this integration, okay, then these mathematical manipulations. You should try them yourself, okay, you should try them yourself. I am leaving it for you, because if I try to explain each and every mathematical step, then it is of no use, because you will become lazy because of it, okay, because you will only idly watch the videos without making the notes. So in order to make you do the work, in order to tell you that you should make the notes, that's why skipping the mathematical steps. But when it will be required, I will discuss certainly. In the steps where mathematical step explanation is required, I will explain certainly. But the places where mathematical step is very elementary, in those cases I will quit the mathematical step. I will not explain it, okay. So you must keep this thing in mind.